Hi everyone, welcome to the C13 lecture. So this is going to cover material that is carbon-13 nuclear magnetic resonance spectroscopy. You will need to understand this, first of all, to do the homework problem or the lab assignment, but also secondly, so that you can interpret the results of the lab that you're doing this week. So you don't need to watch this before you do the alkene lab, but you do need to make sure you watch it and turn in the report before you come and actually collect your NMR data on our NMR itself. So you have these handouts in your manual. They are right behind the biosynthesis of molasses experiment, and they are in front of the alkene addition reaction experiment that you're about to do. So you should find them in there. You also had reading from Fessenden, and Feist, and reading from your actual textbook. And so I'm going to sort of be going between the handouts that you have and then maybe drawing a couple of extra problems on the board for you. So I know that this diagram itself might be hard to see, but this is really just the schematic of the NMR that is in your textbook, so you could find it there if you wanted to. And let's see, what else should we talk about this? This is a topic that comes back into the classroom, so even though you're learning it in lab, you will be tested on it and quizzed on it in the classroom, right? So C13 is sort of an integral part of organic chemistry, so you really have to pay attention and do the practice problems and ask me questions when you are confused. And so on that note, right, I'm not able to start and stop this video very conveniently. And so that means that when I give you a practice problem and I want you to think about it, right, I'm going to say pause the video now, and at that point you should pause your video, right, because then I'm just going to continue on and give you the answer. And if you don't take the time, to actually practice the problem before you hear me answer the problem or answer the question, then you're really not engaging your brain and you're really not learning. If all you're doing is listening and you see the example because I put it up and then I walk you through and all of that, sure, then I know how to do the problem, but that doesn't mean you know how to do the problem. So if I put up a problem and I ask a question, that means pause the video, think about it, come up with your own answer, and then turn the video back on and see how your answer matched my answer. So we'll start here just with the schematic of the NMR. You will see when you come to use ours that really the important part of the NMR itself, and so actually let me just back up for a second. NMR spectroscopy, right, stands for nuclear magnetic resonance. Some of you may be familiar with MRI, which is magnetic resonance imaging. And so the technology or the process or the whole thought of how MRIs work, which you might be familiar with, really came from NMR spectroscopy in the realm of the chemists and the physicists, right? And so what we're going to look at in NMR, using NMR, there are really two types of NMR spectra that we tend to look at. One of them is carbon spectra, one of them is proton or hydrogen spectra. We will save hydrogen spectroscopy for the spring semester and just worry about carbon spectroscopy right now. But you know, instead of calling it NMRI, which is really what it is, the truth is that they did, as always, you have to do sort of a marketing scheme, and so, you know, they asked people, would you get a nuclear magnetic resonance image? And the general populace said no, because the word nuclear to them meant like nuclear weapons and nuclear power and things like that, radioactivity. And in fact, NMR The N for nuclear doesn't mean any of that. The N for nuclear, as you know from your reading, the N in nuclear is really dealing with the nucleus of an atom, right? So again, it's not the nucleus of a cell, it's the nucleus of an atom, and that's really what we're looking at. So the nuclear magnetic resonance is when is that nucleus coming in resonance with the magnetic field. So we will start by talking about carbon NMR. And in fact, you will see that we always write C13, and the 13 goes up here. So hopefully you do know that the mass of almost all of the carbon atoms in the world is 12 AMU, right, or 12 grams per mole. But carbon-12 is not visible in NMR spectroscopy, right? So when we say C13 NMR, we mean that you're only looking at the carbon atoms that have a mass of 13. And for carbon atoms, right, if you were to look at the periodic table, it's 12.01, that tells you that very few of the carbon atoms in our world are actually C13. And the truth is that it's only about 1.1% of carbon atoms that exist in our world are C13. And so those are the only ones we can use NMR spectroscopy to look at. Thankfully, NMR spectroscopy still works for us, okay? But it's really quite impressive that you're only looking at 1% of the carbon atoms that exist in the world when you are running C13 spectroscopy. Proton, all protons, I'll say proton because that's what we call it. It's really hydrogens. Hydrogen NMR, every hydrogen in your molecule is active, so you need very little amount of material to be able to run a hydrogen spectrum. You need a fair amount of material to run a carbon spectrum because, again, you're looking at 1% of the carbon atoms that are in your sample. So here is a spectrum of an NMR instrument. If you look at it, oops, let me get rid of this for you. Right, this is your sample, which is in a very thin tube. You'll see that in lab this week. And this just represents a magnet. So we have a big magnet by our instrument. And you have a north pole and a south pole. And you put your sample down in the magnet, in between the poles of the magnet. And then over here it says radio frequency generator. And over here it's detector or recorder or something. And so essentially what you're doing is you're using these radio frequencies, which comes through all the wires here, and firing that at your molecule. And then whatever is absorbed by your molecule gets recorded by the detector, and you actually get a picture of your spectrum. Okay. So the magnet is crucial for NMR spectroscopy. All right, so we're not going to do a lot of theory, but we do need to do a little bit of theory. And when you have nuclei, right, when you have nuclei in your sample, right, so if you make your sample up in the lab, right, these arrows represent the nuclear spins of the atoms. And so they're going in all kinds of crazy directions, right? Because that's what happens in a random sample. But as soon as you take this sample and you put it into a magnet, right? My magnetic field, which we write as HO, my magnetic field is lined up in one direction. And as soon as I take this random sample of nuclear spins and put them in the presence of a magnetic field, what happens is that all of the spins either line up with the field or they line up against the field, right? They're no longer going in any kind of crazy direction. They line up with the field or they line up against the field, right? That's what's happening. And more of them will line up with the field. That's a lower energy process than against the field. Okay? This is key to the NMR. Because what happens with these nuclear spins try and make sure this is sort of in the middle of the video. Right? And this is magnetic field increasing, right? And this axis is energy. Okay? So you get a picture that looks like this. Yeah, you can see that. All right. And what this diagram represents for you is not a K. What this diagram represents for you is that if I have a certain magnetic field, right, that my atom is feeling, then there's an energy difference between the nuclei that line up with the field and the nuclei that line up against the field. Right? So this is a set energy gap. And this gap is simply between nuclei that are lined up with the field and nuclei that are lined up against the field. And if a particular atom is feeling a different magnetic field, then, maybe its energy gap is larger, or maybe its energy gap is smaller, right? But its energy gap is different. And again, the energy gap is just the difference between with the field and against the field. And does it matter to you what that energy gap is? No. What matters to you is that that energy gap is different for atoms that feel a different magnetic field. And I know you're taking your sample and you're putting it in between the poles of the magnet, and that magnetic field is stable and steady, and you would think, oh, all of those atoms are going to feel the exact same magnetic field. The truth is that they don't, right? The magnetic field that an atom, that a carbon actually feels in a magnet depends upon the environment that that carbon is in. Is it bound to another carbon? Is it bound to an oxygen? Is it double bound to a carbon, right? What is its molecular makeup, right? That changes for each atom in your molecule if those atoms are different. And so that's going to change the energy gap between the with the field and against the field for each one of your atoms. That's what's crucial, because now I have my sample in the field. This exists, right? But the way I get a spectrum is that I flash energy at this sample through those wires, right? And the energy that I'm using is simply radio-generated frequencies. And so this is where you have to go back to Gen Chem a little bit and think about your electromagnetic spectrum, right? What type of energy, what type of waves, what type of radiation has the highest energy? Who remembers their electromagnetic frequency spectrum, right? So the highest energy, you might think of out in space, right, are gamma rays, right? So our gamma rays are the highest energy, and then a little bit less, right? So let me just make a little chart here, right? So out here we have our gamma rays, and I'll put in here where we have visible light, right? So this is energy increasing. But if you have visible light here and you have gamma rays out here, what do you have in here? What's next to visible light? Right? What's next to visible light is UV. And what's in between UV and gamma rays are X-rays. Okay? And so what you should pay attention to when you're thinking about this type of radiation is that UV and above, that's the kind of radiation that creates problems for you, right? You don't break carbon-carbon bonds until you get to UV light, right? So ultraviolet light, that's why it's the ultraviolet light outside that creates the problems with skin cancer, right? UV light can break carbon-carbon bonds, carbon-hydrogen bonds more likely. And so these energies create problems for us. Visible light, right, thankfully, visible light doesn't create any problems for us, because if it did, we would be rearranging ourselves when we walk outside or when we're in a naturally lit classroom or something. So visible light, there is energy associated with it and things are happening, but you're just not breaking any bonds at this point. And so then a little bit less energetic than visible light is IR frequencies. And later on in the semester, I'll make another video about infrared spectroscopy, because that we use infrared light in a certain instrument that you're going to use later on in the semester. And then a little bit less energetic than infrared light are microwaves. And I know some people think that microwaves are really high energy. Microwaves are not high energy. What microwaves do, what infrared light does, is it causes bonds to vibrate, right? Bend and stretch and vibrate. That's what infrared light does. What microwaves do, which is less energetic than infrared, what microwaves do is they allow bonds to rotate, right? So if you have you can see I'm not on screen, right? It looks like I'm stirring something, but whatever. It is just a bond that is rotating. So if you flash microwaves at something, it's just causing those polar bonds to rotate. And so, again, hopefully you're saying, well, how does a microwave work? If you don't know how a microwave works, right, a microwave cooks our food. So you'd think that things are heating up. And they are, right? But the truth is that the microwaves that are being bombarded at your, I don't know, I'll say hunk of steak, right? Or your baked potato, or whatever it is you have in the microwave, right? The microwaves are interacting with those polar bonds, and it's getting those polar bonds, particularly when you think about water, right? You have two very polar bonds with your OHs. It's getting those water molecules to really rotate. And when the water molecule rotates, right, that starts to create friction in whatever it is you're trying to cook, and that friction is what is cooking your food. Okay, so the microwaves themselves are just causing bonds to rotate. And then the lowest energy radiation we have are radio waves. So radio waves, right, when you turn on the radio in your car, it's the radio waves. They are long, slow waves. And of course, we're being bombarded with them all the time. But radio waves are low energy, right? They're very low energy. But that's all the energy we need for our NMR to give us decent data. So it's these frequencies that we're firing at your sample. And that's the kind of energy, that low amount of energy, is all that your nuclei need to do what's called a spin flip. And so, try to stay on screen, right? This, if my atom has this energy gap, right, that's a very specific frequency, right? That's a very set amount of energy. And so there's one radio frequency that is that amount of energy. And if your sample is hit with that frequency, it will absorb that frequency, and it will cause this atom to spin flip. It'll go from the up position to the down position. Right? It'll go from a lower energy to a higher energy because it absorbed that frequency. It absorbed that quanta of light or radiation. But a different atom has a different energy gap, and so it needs a different frequency. If I call this 1 and 2, excuse me. It needs a different frequency in order to spin from with the field to against the field. And so what we do in the NMR is we take a really wide range of radio frequencies and we fire that at our sample. And so ideally our sample can pick whatever frequencies it needs in order for these nuclei to spin flip from, and again, spin flip is when it's with the field to against the field. We just call that a spin flip. It's not exactly what's happening, but we're going to not worry about that till advanced organic. Okay? So what we're looking at when we ultimately look at a spectrum is we're looking at what frequencies were absorbed by our molecule. Right? You're going to see peaks that represent this frequency and this frequency and this frequency and whatever frequencies your molecule happened to need in order to spin flip. And that's what you're going to see on your NMR spectrum. And that's all the theory that we are going to cover at this point. So, you have this picture fight with the screen, are we? Okay. You have this picture of a spectrum. Let me lower it down. That's good. There we go. In your packet. So go ahead and make sure you find that in your manual. If you don't have your manual handy, pause the video and find that particular picture. All right. This is a typical NMR, carbon NMR spectrum. And so when we talk about spectra, and you look at spectra on a screen, you're going to notice that 0 is here, and then the numbers increase as you go across the screen that way. Okay, so for a carbon, we traditionally run 0 to 200. And these numbers are called our chemical shift. And we either use delta, right, the Greek letter delta, to represent our chemical shift. If we wanted to say this peak is at, I don't know, 53, we would say 53 delta units, or delta 53, or we could say 53 ppm, right? You can either say delta units or ppm. That is your unit associated with the chemical shift of a peak. So we start at 0, and every instrument is different. And so in order for us to have a chemical shift that is reproducible, what we use is an internal standard. And our internal standard for really for any NMR spectroscopy is called TMS, right? And TMS is tetramethylsilane. So it's a silicon group with 4 methyl groups, tetramethylsilane. Right? And we use TMS because it causes our methyl shift to be very far, I'm going to say right now, to the right, because we haven't talked about the words yet. But we label that 0. So that is something that you have to put into your sample, right? It's not a peak of your sample itself. It's something you put in the sample so that you can tell the instrument to go to that peak and set it to 0, and then all of the other peaks will have the appropriate chemical shift, whether you're using an instrument here, or you're using an instrument at Harvard, or you're using an instrument at Argonne National Labs, or wherever you're using an instrument. Okay? And so here's TMS, our internal standard. This is our chemical shift. When we talk about areas of the spectrum, we talk about this end of the spectrum near TMS. We talk about this as the upfield side of the spectrum. And we talk about this end as the downfield side of the spectrum. The higher the numbers, the more downfield. And so there's not a cutoff. There's not a place where it's upfield or downfield. But we use that to talk about peaks. And so if I look at the spectrum, I can see 1, 2, 3, 4 peaks. And I see 4 peaks because 4 frequencies in my molecule, when I flashed that whole band of radio frequencies at my sample, 4 of them were absorbed. So whatever frequency was absorbed, you're going to get a peak for it. And so in this case, I see 4. I don't care what the energy of the frequency was. I care how many do I see and where do I see them on my spectrum. And so I see 4, because remember, I'm not including TMS. TMS is not part of my molecule. And if I were to describe this spectrum, I would say that I have 3 peaks that are upfield and 1 peak that is downfield. But I could talk about these two peaks and say that this peak is downfield from this peak, right? Or I could say this peak is upfield from this peak, right? And so we just use those words to talk about the spectra relative to a chemical shift. So that's downfield, upfield, your TMS internal standard, your axis. And again, what you're looking at are the number of peaks, or they're often called number of resonances, that you actually see in the spectrum. So we're going to be concerned about how many peaks you see, and we're going to be concerned about where you see them. What's the chemical shift? This chemical shift is pretty far downfield, right? What's the chemical shift, and what does that tell you about the structure of your molecule? So the reason NMR spectroscopy is so important is because if you have a proton NMR and if you have a carbon NMR, you really can use that information to figure out what the structure of your molecule is. It's really, if you interpret these things properly, it's really quite incredible. We're going to use NMR, or not NMR, we're going to use IR spectroscopy later on in the semester. IR spectroscopy is great, right? But what it tells us are functional groups, right? So if I want to know what functional groups are present in this mysterious white powder that I have, then I would take an IR spectrum of it and I would interpret those and figure out what functional groups are present. I wouldn't know where they are, I wouldn't know the structure of my molecule, but I would know what functional groups are present. If I wanted to figure out the molecular weight of my mysterious white product, then I would run something called mass spectroscopy. We'll talk a little bit about mass spectroscopy second semester. Not first semester, but that we traditionally use to tell us the molecular weight. And if we know the molecular weight, then we might know approximately what the molecular formula is. But then we still don't know what the molecule looks like. And that is where C13 and proton NMR come in, and you really start to build your molecules together by interpreting the data that you get in those spectra. And so that's why organic chemists really use NMR is our go-to tool for virtually everything. Okay. So, you have that picture. Let's go now to the next picture in your book. And that should say alkane series C13 NMR spectra on it. Is that easier or worse to see? I'm sorry, you're going to have a close-up of me. Okay, maybe we'll go with that. But it doesn't matter because you have this picture yourself. So, here are a couple of molecules, and let's see what these spectra tell us, right? So in this case, you can see that there's a peak at TMS, which is 0. Right? So I know that's TMS. I use that to set up my the axis of my spectrum, and now I don't have to worry about it. It's not a peak in my molecule. But if I look at this first case, right, I have propane. And if I look closely in here, you're going to see that you actually have two different peaks that are very close to each other. But there's still two different peaks. And so that means if I put propane in an NMR tube and I take a spectrum of it, this is what I see. I see two peaks. But how many carbons, and again, remember, we are only looking at carbons. So how many carbons are present total in propane? And of course, you're saying to me the correct answer is 3. There are 3 carbons in propane, and that is true. But what you see are just 2 peaks. Okay? And so here's where you think about the environment that carbon atoms are in. So I'm going to turn the lights back on. Try to get rid of that. And so when I think about propane, and again, it doesn't matter if you can see the spectrum underneath this or not. In fact, we'll get rid of the spectrum, but you should keep yours in front of you. But if I look at propane, right, I have a CH3 group and a CH2 group and a CH3 group, right? And what I'm trying to look at is which carbons in my molecule are different from other carbons. And so if I look at this CH2 group, I'm going to guess that you can say to me very easily that a CH2 group is different from a CH3 group, right? And that is true just because it's bound to different atoms, right? So a CH2 group, CH3, these two are going to be different from each other automatically. And so now the question becomes, let me just be clear for a minute. We are not simply looking at whether our carbon atoms are CH3 or CH2 or CH or C, right? Because that only gives us 4 choices, and we have many more peaks than that in our molecules many times, or in our spectrum many times. So don't think you're just looking at CH3 and CH2, but you are looking for which atoms are different in your molecule. And so CH2 is clearly different from a CH3. But if I look at this CH3, and I look at this CH3, are these two CH3s, are these two carbons different from each other? This one's bound to 3 hydrogens, this one's bound to 3 hydrogens, and they're both bound to the same CH2 group. And so I can see a plane of symmetry that runs right through the center of my molecule, that this side is the same as this side. And if these two carbons are the same, then they'll absorb the same frequency, and they'll show up as one peak in my spectrum. So the number of peaks that you see in your spectrum often indicates whether there is symmetry or not in your molecule, and we use that when we're building molecules. And so for propane, I'm only going to see 2 peaks in the spectrum because that's the same as that, and that one is different. And so I'm going to see 2 frequencies that are absorbed, and in fact, that is what you see on your spectrum. Now look at butane, right? When you look at butane, how many different kinds of carbons are in your molecule? Again, we're looking for symmetry. So it might be hard to see here, but if I were to redraw my molecule, so it looks like this, right? Still butane. But maybe if it's drawn like this, you might be able to see that there's a plane of symmetry that runs through the center of my molecule. And that means that this carbon is exactly the same as this carbon, right? 2 hydrogens, a methyl, and a CH2, 2 hydrogens, a methyl, and a CH2. Right, so they're exactly the same, and then this carbon, is the same as that carbon. So for butane, I would also expect to see 2 peaks or 2 carbons in my, or 2 resonances in my spectrum. And if you look at your sheet, you do, right? You see the TMS peak, and then you see 2 other peaks. Let's talk about pentane. Here's pentane. How many peaks do you expect to see in pentane? I can see that that's right where the glare is. CH2, CH2. Are these 2 CH2 groups the same? And hopefully you've answered no, right? This CH2 group is bound to a CH2 and a CH3. This CH2 group is bound to a CH2 and a CH2. So even though they're both CH2 groups, they are different from each other. Their environment is different. What's bound to them is different, which makes them different, have a different magnetic field that they feel, and then therefore a different in their spin flip energy requirements. Okay. So this carbon, so again, let's just go, and ideally you can see the plane of symmetry is here. So this carbon is in fact the same as that carbon. That methyl group is the same as that methyl group. But this carbon in here is different from either of the other two. So in this case, you're going to see 3 peaks in your spectrum. And that is in fact what you see. And again, you can pause this video anytime to really have a closer look at things. I think the last example you have is hexane. Again, might be difficult to see any symmetry when drawn like that. But if I redraw it like this, you can see symmetry. And so that is the same as that is the same as that. And those 2 carbons are the same. So I'd expect to see 3 peaks here. So for practice, I would like you to tell me how many carbon resonances you would expect to see for heptane, and then for 2-methyl-butane. So stop the video here, draw those 2 molecules, figure out if there's a plane of symmetry, figure out how many different carbons are present in those molecules, and then write that answer down. Pause. Wait. All right. So welcome back. Hopefully you could see that there were 4 carbons in your 4 different carbons in your heptane molecule. That's the same as that. That's the same as that. That one is the same as that one. And that one was different. So there are 4 there. This one was a little trickier, right? And so if I look at this molecule, I see a CH. And I don't see any other CH, so I know that's going to be different. And I see a CH2, and I don't see any other CH2, so I also know that's going to be different. But now I have 3 CH3 groups. And the question is, are they all the same as each other, or are they all different from each other, or are some of them the same and some different? And maybe you can see that that one is in fact different from the other 2, because it is bound to a CH2 group. And these are bound to a CH group, right? So this is different from these other 2. But this one and that one are exactly the same. And they're the same, because remember, these are all rotating around, right? That's what they do at room temperature. This is a CH3 bound to 3 hydrogens and a CH. CH3 bound to 3 hydrogens and a CH, right? So these 2 groups if you get to the same point, then the rest of the molecule is the same for them. And so these two are actually the same as one another, even though one looks like it's closer to the ethyl than the other. Right? They rotate all around, so one is not truly closer to the other. And these two CH3 groups, or those two carbons, are the same. So I would see 1, 2, 3, 4 different carbons in this molecule. And thus far, you've only had to go 1 carbon and then they're the same, right? You can go more than 1 carbon. When you're trying to determine if 2 carbons are different from each other, right, you have to follow the whole molecule out. And if you don't find any difference when you follow the whole molecule, then they are in fact the same. But if you find a difference 8 carbons away, then that means that they are different from each other and they will have a different resonance, and therefore you'll see a peak for them. So it's not just the immediate environment, it's all the way through the molecule. Is there a difference that those carbons feel? Are there patterns or substituent patterns or whatever different, or are they the same? And so to that end, do one more example. All single bonds. I'm just trying to make it darker for you to see. Okay, so now take this molecule, and here's a typical exam question. Right? How many different carbon resonances would you see in the spectrum for this molecule? I'll lift this up just for a second, because I realize there's a little. So pause the video now and tell me how many different carbon resonances you would expect to see in the spectrum of that molecule. And then when you come back, the answer is that you should see 10. 10 carbons, 10 peaks. You will see 10 peaks. And so that CH3 group is the same as that CH3 group. And the question is often, is it the same as this one? Well, CH2, CH2, CH2. But then these two CH2s meet. And so that branch is exactly the same as that branch, because then they go through the rest of the molecule together. But this carbon and this carbon are not the same, right? This carbon has 2 ethyls. This carbon has an ethyl and an isopropyl. So if these 2 carbons aren't the same, then these 2 carbons aren't the same, and those 2 carbons are not the same. And so I'll use that. Square, and I'll use a triangle. Right, so these 2 are the same and these 2 are the same, and this one's different and it's different from this one. And we know that this ethyl group is different from those ethyl groups. So we have that so far. And then these 2 methyl groups are the same as each other because they're methyls and then they meet. So it doesn't matter which way they go from there. So these 2 are the same. Stars. And these 2 are different from these 2. because these two are bound to a carbon with no hydrogens, and these two are bound to a carbon with a hydrogen. So that makes this carbon, which will make a sun, different from this carbon, which will make a solid square. And then these two are the same as each other, right? But different from those two. And then we had already determined that this one was different from that one and anything else. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different carbons. Okay? So this is the type of problem that you will see on your test and quiz. You have to look for either whole symmetry in your molecule, which there's not a complete plane of symmetry anywhere in this molecule, but there are little bits of symmetry. These two are the same. These two are the same. These two branches are the same. So there's little parts of symmetry in your molecule, just not a completely symmetrical molecule. Right? So start looking for planes of symmetry. Start looking for little parts of symmetry. Okay. Let's now go to the next page in your notebook, which starts with the aromatic ring C13 NMR spectroscopy. I'm trying to make this dark again. So you have these three spectra, and on the bottom, it's hard for me to see there, okay? So on the bottom, you have compound A, which I have named 1,2-dichlorobenzene. Compound B is 1,3-dichlorobenzene. Compound C is 1,4-dichlorobenzene. And it doesn't matter what the names are, just call this A, and call this B, and call this C. And another thing you don't have to pay attention to right now, because you will learn that in an aromatic ring or in an arene ring, the position of the double bonds doesn't matter, only in that kind of ring. And so for right now, you can just ignore that there are double bonds present. And so what you need to do is you need to match compound A, B, and C with these three spectra. So one of the spectra has 2 peaks, the middle spectrum has 4 peaks, and the bottom spectrum has 3 peaks. So look at your spectra and look at your 3 molecules and try to find, right, there are 6 carbons in benzene, and none of these have 6, which means there must be some kind of symmetry in these molecules. So you need to draw your plane of symmetry in each one of these molecules and figure out how many different peaks each one of these molecules would have. One of them has 2, one of them has 3, and one of them has 4. Figure out which one of them has what, so that you then can match A, B, and C with these spectra. So pause the video here and work on that problem. And so I just redrew the 3 molecules for you so that we could look for planes of symmetry. And when I look at this molecule, I see a plane of symmetry running right through there. So this carbon is the same as that carbon. That carbon is the same as that carbon. And those 2 carbons are the same. So the compound A, 1,2-dichlorobenzene, I would expect to see 3 peaks in the spectrum. For the 1,3 sample, my plane of symmetry runs there. So this carbon is the same as this carbon, and that carbon is the same as that carbon. But remember, you have a carbon here and you have a carbon here, and these 2 carbons are not the same as each other, right? This carbon is near something that has 2 chlorines, this carbon is not. And so that would be a 3rd type of carbon, and that would be a 4th type of carbon. So in the 1,3 case, I would expect to have 4 carbons. And then in my last example, I have a plane of symmetry there, but I also have a plane of symmetry here. So I could take this molecule and fold it in half here and then fold it again. And so that carbon turns out to be the same as that carbon, right, if I just fold it over. And if I fold it and fold it again, you will see that this carbon and this carbon and this carbon and that carbon are all the same. And so this molecule would have 2 peaks in its spectrum. And so now I can very easily say that the spectrum on the top of your sheet with 2 peaks is this compound, the middle compound with 4 peaks is B, and let me make sure I'm reciting these for you correctly. Oh, I'm sorry, yeah. So your middle spectrum does have 4 peaks on it, so it would be B, and your bottom spectrum has 3 peaks, and so that would be A. So that would be C, B, A as you go down the list. All right, that is symmetry, right? Symmetry is important. The next sheet that you have in your notebook are 2 spectra that you've seen already. The top spectrum is just pentane. The bottom spectrum is 1,3-dichlorobenzene. And the reason I've put these on the same piece of paper in your notebook is because I want you to pay attention to chemical shift. Right? So far we've been looking at, is there symmetry, is there not symmetry, is there complete symmetry, is there partial symmetry, right? That's important. The other thing that is important in C13 is what is the environment of these carbon atoms. That's what chemical shift is. And so we weren't really paying attention to the chemical shift when we were talking about, I can see that's, right, we weren't paying attention to chemical shift when we were talking about how many peaks there are, right? So both of these things are important, but we're just doing part of it at one time. And so for pentane, we said there were 3 peaks, but look at their chemical shift, right? Right now they're between 15 and 35. So they're very far upfield, right? They're close to TMS. On the bottom of your spectrum, you have the aromatic compound. And I can't see it on my screen here, so I'm going to move it up a little bit. If you look at where these 4 peaks are, they are about 128 to 135 or so, right? Almost 100 ppm further downfield. And so the truth is that when you're paying attention to chemical shift, right now this spectrum runs from 0 to 75. This whole spectrum would actually be to the right of 80 to 140. So even though they're sort of in the center of your page here, they have very different chemical shifts. Alkane-like carbons that only have carbon-hydrogen and carbon single bonds, alkane carbons are always going to be found upfield. Aromatic or arene carbons are always going to be found in the region of 110 to 160, right? They're pretty far downfield. And so we use chemical shift to start telling us about environment. So if I tell you that there's a peak on your spectrum that shows up at about 10 ppm, you should instantly say that that is an alkane-like carbon because it's so far upfield. And if I tell you you have a peak around 130, you should tell me that that's an aromatic or an arene peak, and you should be able to tell me that it is definitively not an alkane-like carbon. Right, so now we're going to pay attention to chemical shift. And so to start that discussion, you have a paper, I think it's the next page. Try to not be weird on this video and look closely. Right, you should have a piece of paper that has ethylbromine and ethylamine and ethyl alcohol on it. And what I want you to notice from these spectra, right, all of these molecules have 2 carbons, and those 2 carbons are different from each other. And the CH3 group that is furthest away from the heteroatom, right, that CH3 group really doesn't change its position very much, right? It's all in a row. And so we would call that an alkane-like carbon. It's pretty far upfield. It only has hydrogen and carbon single bonds. So this carbon right here is the one that is showing up and not really changing its position very much. But the carbon that is changing its position is the CH2 carbon. In this case, the CH2 carbon is bound to a bromine. And so that pulls it a little bit further downfield, right? So now I'm at about 28 or so. But when this carbon is now changed, or when this bromine is now changed to a nitrogen, when I have a carbon bound to a nitrogen, you can see that that pulled it even further downfield. So now I'm about 37. And if I change the nitrogen to an oxygen, my carbon that's now bound to an oxygen moves all the way down here to about 57, right? So this second carbon is the one that is moving down because the second carbon is the one that's bound to the atom that's changing. And so you might say, oh, maybe this is electronegativity related. It is partially electronegativity related, right? It has to do with where are the electrons in that covalent bond. But what you should pay attention to is as I change the heteroatom from a halide to a nitrogen to an oxygen, I'm really pulling that carbon downfield away from the original alkane-like positions. The next handout that you have is really just more examples of that for you. What I did in each one of these molecules is the carbon that I put a little arrow next to. That is the carbon that is furthest downfield. So in the first case, again, this is your functional groups, you have an ether molecule. The carbon, this one happens to be symmetric, but the carbon that is bound to the oxygen, we just saw that. The carbon that was bound to the oxygen in ethanol got pulled downfield, right? That's what's happening here. Right here you see a peak at 73 or so, right? So that carbon is the carbon bound to the oxygen. Now I have an alkene, right? The 2 carbons of my alkene, they're back down in this region above 100. That starts to be like the aromatic region. And the truth is that the aromatic region and the carbon-carbon double bond region, so the alkene and the aromatic, the alkene and the arene, those regions actually overlap each other. So without any further information, if you just tell me you have a peak at 154 ppm, I cannot tell you whether that's a double bond or whether that is an aromatic ring, right? Those regions overlap each other. We'll talk about all of this, right? But that's This carbon here that's pulled furthest downfield has the arrow. And the next case I have an ester, right? Which means I'm pointing at the carbon of the carbonyl.